So what I'm going to do today is I'm going to go through some larger examples of user interfaces, or also how you can implement them uh, in different ways. So the first one is a very simple one. It's a weather reporting application. So what we're going to do now, we are going to use some of the free services we have in Sweden for requesting weather data. And if we look here on the source code here, we have a URL. It's called Open Data Download metfsct smhi.se. That is a URL where you can, it's an open API where you can query weather data. And you put it together by calling this address, and then you specify a certain URL. And in the curly brackets here, we put in what we want to have, what kind of weather data we want to get, longitude and latitude, and then we get a JSON file back. So this problem here, you need to go to the internet and request data, and then we need to parse the data and provide some kind of data that we can use in a user interface. So I've decided to separate the logic of the application into separate class here. In this case, an SMHI class. It has a constructor where we have a default longitude and latitudes given. So if the user doesn't say anything, it will have these longitude and latitudes set by default. We set several attributes here. So the URL, of course, an API template that we're going to use to actually retrieve the data. We have the category of data and all these things we need to fill the API out. Those are kind of default set here. Then I have a method here to request the forecast. And that is the kind of main functionality here. So all the accessing web pages on the web is usually done through a special module called requests. And that is what we are going to use to get the data from the web. So in the first step here, we create our API string. We use our template here, which we have here, to create the exact specific URL. And then we call the request here. So request have a method called get. Basically, it's the same thing as you're opening a web page, but you're actually doing it programmatically. And the result will return back as a string. So this is the string SMHI info. That string is actually a JSON structure. So what we can do then is use our JSON module here to load that into a string. So here we do SMHI load, and then we take the text we get back from this requests object. And we store that in the self forecast attribute of the class. That is one thing you do when you instantiate. You get the kind of the current snapshot of the data, and then we have to be able to access the different data structures. The JSON file contains multiple fields, so we need to be able to extract those. And one method that I have added here is parameter names that queries the JSON structure for which parameters that are contained within the loaded data. And then I also have a method called parameter values, and then you can specify the name of the data you want, and then you get that data back with dates and values. And we can run this here just in the main program here in the same module here, just to see how it works. In this case, it just plots the data here in a matplotlib directory. Let's see if we can clear this. Just print out some of the data here. See how it looks. So you can see here that the data is a dictionary here consisting of, here you have the parameter names, and here you also have, this is the list of parameters. let's see if we can just print out the actual JSON as well, just so you can see how it looks. So you can see that you have a dictionary here with the different values, and you have also values inside here in the dictionary. So we query that data and we create values that we can plot later on. So if we now want to create a user interface, so we need to kind of create a UI file first. And what we are going to do is we are going to combine a matplotlib view with a Qt user interface. So what we are going to do in the Qt creator, we are going to create everything except the view itself. So we go in here. So you can see here that we have a main window. We have a label here. We have a combo box that we'll use for selecting the parameter. We have a longitude label where you can enter the longitude and the latitude text box here as well. The important thing is that those things that we want to interact with in the user interface, we should give them proper names. In this case, we have param combo. That is the name of the combo box. The line edit here for the longitude is long edit. We have lat edit as well. And we have a refresh button here to kind of forcibly load a user interface. But basically, we don't do much more than that. We also have a outer horizontal layout, which we will add our matplotlib to. So basically, this is what we have here. And then we will add our matplotlib here in the bottom here. Basically, if we take a frame here and put this here, you can see that we'll put the matplotlib in that part here, but we'll do that from the code itself. We'll save that here, and we go back to our user interface. So then we create a weather app Python file. We import what we need here from Qt. We also this is the more complicated part to get the integration with matplotlib working. So what you need to provide for matplotlib here is what's called a backend, something that you can insert into the UI, and those are included in this module here, Qt5 or Qt6 ag. And then we want to import a figure canvas and a navigation toolbar. So figure canvas is actually plot. It's a separate widget, and then you also have a toolbar that you can get. That is the toolbar that we have in Matplotlib, and those we import them in more understandable names. We need to import some stuff from Matplotlib, and we add a NumPy here because we need it. And then we import our SMHI module. So this separates the user interface from the model itself. So we can rewrite this user interface to be a web interface, for example, and then or another user interface toolkit. So we don't have to rewrite that if we do a new application. So what we do here, we load our UI5 here to create the user interface. We instantiate SMHI model, this class here, we instantiate it so we can query the weather. We set the current parameter here, which is the default, so like the temperature. We create a figure, Matplotlib figure. We create a figure canvas here, and here we provide the figure to the canvas widget. We create a toolbar where we provide a canvas and who is going to own this widget. And then in the main widget layout, we add the widget self canvas here to our user interface. So remember now we already have loaded all our own user interface widgets up here. So now we can add these extra user interface widgets from Matplotlib here using this add widget self canvas and self figure toolbar. We also need to connect when you select the combo box. We need to connect a signal when you change the combo box. So that we do here. So the param combo was part of the Qt Creator user interface. It sends a signal current text changed. We connect that to our own method here, self on text changed. We also need to connect the button. So self refresh button. It has a signal called clicked. We connect that to self on refresh. So on refresh will refresh the user interface and update and load a new model as well. We have some methods here that we call. So request forecast is the method in our user interface that will call our SMHI object, request a forecast. We have what we discussed in the last lecture, a way of updating our controls. So it will take the information from the model and update the user interface. And then we do the plotting in matplotlib. So we have three methods that we implement. So update controls will fill the combo box with the parameters that we have from the model. And we add them to the combo box. And that's also important when you use combo box that you start with a combo box clear, and then you add a parameter. Otherwise, the combo box will fill up completely. We also set our longitude and latitude, what we get from the SMHI model object. The update model takes the text that we have in the user interface and assigns them to our SMHI model here, like this. And also changes the current parameter to what we have in the current text here. Then we do request forecast. And here we select the parameters we get here, and then we do, why we do that actually? No, anyway. But we put self-current parameter here, which is the user have selected in the combo box. And then we get back dates and times, which we store in our user interface in the window class. And then we have the plot routine here. So it updates the model again, and then we do figure clear. We get our axis objects and we plot our data here, create our diagram. We draw here. Something we need to do here in the user interface, we have to flush event so that it actually forces the update of the diagram. We have a refresh here method that can be reused so that we update model, request forecast, and then plot. Our connector here, the slot here for our refresh button here could just calls refresh. On text change, that changes the current parameter and calls refresh. Our main application is very simple. You create an application object. You create a weather window. You show the window, and then you start the application loop. So running this will produce something like this. So this is the widgets we inserted into our user interface from Matplotlib. This is the toolbar that is provided from Matplotlib. Here you can see here that the combo box contains all the parameters in the model. So we can do wind speed, for example. We can also do refresh here. And we can change the parameters like this. So this is a simple way of how you can implement the application if you have a model like this. So it's always good to separate your simulation model or anything else that you want to do in a separate class, and then the user interface part you implement separately. So this is the model, and this is the view and controller that we discussed here, this concept of user interface. So this first example I want to show. Then I have a second example how that's a bit more, it's a larger application. So it's a beam application. And what I'm going to do just first to start with to show how this application looks like. So this is a more completed engineering application. So it's for computing a continuous beam. So that is a beam that is fixed on different supports like this. So you have this is a fixed support which can rotate, and then you have a 2-meter beam here, and then we have a rotating fixed support here that can move in the X direction, and it displays here the deflection of the beam and section forces and the moment of in the beam, and there you can it will also visualize the loads. On the left side here, you have a tabbed interface here for the different parameters. So if we want to change, for example, the first section here, we want it to be 3 meters. We can check here. It should update, but it didn't. Yeah, okay. There was some refresh update and it didn't work. So you can change things here. You can also change if you want to have a fixed position here on the left side. I'm not sure why it's not updating directly, but okay. So this is the beam. So I decided to make this as a single user interface where you have there's not so many separate windows here. So every setting you can set here using this tab. You can change which beam you are working on by selecting drop-down box here. There is also options here for which should update directly, but don't. To select the different results here. You can also get the table of the results like this. So I'm just going to show basically how you have implemented this. So everything in this is also centered around a model. So I have a beam model, which is the simulation or the actual where the calculations are performed. So in this case, I'm using a special toolkit called CALFEM for Python, which I import as CFC. So that contains all the structural mechanics components. I also use a logging framework here. But basically here, this is the main class here, the beam model. It has notation here. So these are just constants that make it easier to read the code. So fixed y is the boundary conditions. I have 3 of them. So fixed in y direction, fixed in x and y direction, and fixed in all directions. Some default material properties. These are constant. These are available for every instance of beam model. They are the same. In the constructor, I have created a just called new here, which is corresponds to when you create a new model, it will initialize all the parameters to default ones. So you can see here that I have a new here. I initialize the default properties here, which returns this one here. And I just I have a list here that contains the length of the segments. These are the computational points along the segments, and these are the supports that I have implemented. I also have a list of the loads for each distributed loads for each segment, and the material properties for each segment. I set up some standard attributes here. So these one here with none, these will contain values for x and displacements and rotations, and also the section forces and moments. And I have a method here called solve that will compute a solution to this problem. We also have some methods here for adding and removing beam segments. Solve basically sets up the problem. This is just structural mechanics, so I won't go too much here, but it will solve the problem. It uses NumPy to solve the problem. It loops over the elements, assembles them, sets up the boundary conditions. Here you solve the equation system, and here you compute the result forces back. The model also implements that you can save the model as a JSON file. You can also open the model from a JSON file. So basically, it contains the entire beam model and all the functionality that we want in our application, but without the user interface. We also have properties here that returns different aspects of the model. So here you have like total length, max load, mean load, and then you can use them as attributes. You don't have to call them as functions. Now we can see how if we just run this, I usually have this kind of method of if I have a model like this, I do a simple test case in the plot, so I can run the model here and see how it works. And there's not so much output here. Let's see. I don't have a printing state here, but so running this will solve the problem here. I can do a print beam.nvm. You can see how that looks like. So here I get back a NumPy array with different normal forces, section forces, and moments. We can also print X here, which will return the X positions on the beam. So if you look at the class overview, we can see here that we have when we now are implementing this, we are going to implement from the main window class. So we will have a menu. We also have a beam window. That is our own class that we derive from main window. So that is our main application window. Inside our window, we will have a Q widget. Sorry, we will have two main classes here. We will have a draw widget that is the so here, okay. So we will have a beam widget that will visualize the beam, and that is inherits from a draw widget, which I have implemented separately to handle drawing in a more easy way than yeah, it simplifies the drawing here. So we have a beam widget that is our actual view, customized beam visualizer. This is a generic drawing widget that has commands for drawing. We have a separate result window that will implement this result table. So the beam window will have one beam model. So it owns one of these. It will have a beam widget, which is our visualization component, and a result window. So the beam window will be the composition of several instances of objects, mainly beam model, beam widget, and result window. And beam model is the only one, that's the one that does all the functionality. So let's look at them. Let's look at first the draw widget. So this is a special widget that I derived from the Q widget class in Python, in the Qt, and then it is a instead of drawing in pixels, we can draw in world coordinates. So when we can draw the beam in the actual size the beam is, and it will scale. So that's why we have some coordinate scaling here. We have some internal state here for what kind of colors we are going to use. We create special pens here. That is the way you work with drawing in Qt. You create pens and brushes, and we will do that setup so we don't have to we can use a different syntax to draw that is more simplified. Update, it will scale the coordinate transform, and it will redraw the system here. This is how we update the canvas here for drawing in world coordinates. And here is the painter setup. And then we have the paint event. So paint event is called when you create your own widgets. They will be you have to implement the paint event, and where you will draw your own widget. So what we do first is we let if there is a drawing method drawing event functionality in our derived class, or where from the class we inherit from, for this case Q widget, we call that. We fill our rectangle here with white, we call our own drawing method here. So we will delegate to our, this class is not meant to be instantiated itself. You should derive functionality for this class, and then we delegate the drawing down to this onDraw method. And then we tell Qt that we are done drawing. So what we have to do on our class is re-implement this class only. All other mechanisms is hidden away from us. And this is what you usually do when you do object-oriented, that you want to be able to reuse code. So if I want to do another application, a frame application, we can use this draw widget for a drawing in our next application as well. And we have some, what happens if you resize the window, we need to be able to resize the drawing. So we need to update the coordinate transform, and so on. We also have some communication functions here for converting to and from window coordinates. So if we have an integer or a coordinate pixel, we return a floating point coordinate here. And here you can also see something I haven't talked too much about in the course, type annotation in Python. So I said before, Python doesn't have really a type. Types are assigned during assignment or determined at assignment. But if you want to enforce that you only want to have integers to a function, you can actually do :int, colon int here, and that then the interpreter will actually do a check that you don't call that function with the incorrect data types. It can be useful sometimes. And then you can also make sure that it returns a q.f, a certain data type as well, using the arrow notation here. It's an optional syntax, but it can make your code more redundant. Here below, I have implemented several drawing functions that make it much easier to draw in our window. So I have a polygon, I have a line, I implemented an arrow, I implemented a rect, circle, and a triangle, and also a text drawing function. Some convenience properties here for our colors for the pens. So this is the main functionality, main kind of generic drawing component. So then I specialize this into a beam widget. So you can see here I inherit from draw widget in this case. I call draw widget's initialization. And here you can see the draw widget is dependent on a beam model. So here we draw, we kind of get the data we want to view, and that's beam. We store a temporary reference to that in our beam widget. We set some constant here how large different things in the drawing should be. Here are some flags. So if we want to draw loads, do displacement, moments, section 4, and dimensions, we can turn them off and on. We have some flags for that. We update the scale factors, depending on how many beams we have in the model and how long there are, we update the scale. And then we have, I divided up the drawing in different methods here. So we have draw beams that will draw the beams. And you can see here that I loop over the beams in the beam model here. And then we also have self line. This is the functionality from the draw widget. Draw dimensions, a bit more complicated. But you can see here I use the methods from the draw widget class here to implement the drawing, and that simplifies things a lot. Draw support, same thing here. We check what kind of supports we have in the beam model, and then we draw the different supports. Draw load, something here. Draw moments. And then you can see here is the actual onDraw function, and that will be called from the draw widgets, depending on the paint event. So this is what we have to kind of override to implement the drawing. And you can see here that by putting these drawing in different methods, we can turn them off and on quite easily here in our drawing method. Draw supports and draw beams will always be drawn, so we don't have a flag there. Dimensions is also optional, and we do that later on. So you can see them as layers that you stack on top of each other. Draw support, draw load, like this. So this is our draw view. We also have here same thing, properties to get certain data from that. Our main beam window application here. we inherit from main window like this, and then we do set up our constructor. I have a special function here to set up the user interface, mainly to not create a too large constructor. I set up some default values for different things here. The file name here is the current file name that we our open model. Here we have a beam model. Instantiate that. We create a beam widget here. We give it our beam model, and then we add this widget to the screen, to the user interface. We create a new model. We set some properties here. We connect all our signals here. In this case, you can see we have actions triggered, and we connect them to our own methods here in our class. We have a lot of actually signals and slot connections here. Segment combos, segment lengths, count points. We connect them to different parts of our window code here. Setup UI, very easy. We load your user interface file from a UI file. New model, we use the functionality in the beam model as much as possible. So we tell beam model, let's create a new default beam. We update our controls. We update our combo. We set the current index to which beam are you looking at here, with this one here. We call on model updated to beam widget to see what that does here. Yeah, okay. So we that's what to be able, if we load a file from, we need to be able to update the scaling. So that's why we tell the beam widgets has been updated. Update controls. Here we go. Take the values from the model and we update the user interface here. So we fill our we get our material properties. We create the strings and we set the strings in the controls. Here we can also see that we say we have radio buttons here. We need to be able to check what is said in the beam model, and then we call check on the different controls in the user interface. Update combo, we clear it, we fill it with data here. We also do update the text in the list boxes. Edit finished, we convert from the controls, and we update the beam model as well. So we do, you can see here we do try float here again, the same thing I show you in the lecture here, to make sure that we have a robust conversion of floating points from strings. And here you can see we update the beam model itself. Same here, we check the different option boxes in the user interface, and then we update the model in this code here. And when we have updated the model, we need to solve it. So we call beam model solve. We tell the beam widget it has been updated, and then we update our controls, our labels, and if we have a result window up, we update that as well. We have open here, so we use a file open dialog as I showed you yesterday to open the model. We can read JSON files and different files here, and then we do beam model open from JSON. So now we load the model by just telling the beam model to load another one. We need to tell beam widget that we have a new model so that it updates the scalings. We update the controls, reflect the currently loaded model. Same we do the other way around. We use save as JSON. We don't have to do anything more than that because the user interface is already up to date. Save as, we ask for a file name, and the user can save it as a different file name. Here are some signals for slots for handling, turning on and off different aspects of the drawing. And you can see here we just set the properties show moments, and that will handle the update automatically. Add a beam, we use the functionality inside our model. So we have add segment, and we add a segment to the beam. And then we have on model updated, and that will tell the beam widget again to update the coordinate transform. Update combo controls, So you can see we delegate a lot of functionality to other classes. That makes also the user interface code more manageable and easy to read. The final thing I want to show you there is also result view. And that is so if I run the code again, let's see here. There's a table here, this. So here you have a table of the Beam values, and I will show how that is implemented. It works basically the same way as the Beam widget, but it's a standalone window. So here we derive from QWidget instead of QMainWindow. You can see also we pass over the Beam model here because that is the information source. We assign it as an attribute value in our window class. We load the user interface from the result UI file. We set some flags so we get the tool window. And this one is interesting here. Window stays on top. That makes sure that this window is never behind the main window. So it stays on top all the time. And that can be useful if you have these kind of tool palettes. We update our table, and that here is the interesting function. So result table is the one that's part of the UI file. We set the vertical header to be visible. So we set the row count to the shape of the result values, and we set the column count to 5. And then we can also set the horizontal header labels here. We give them as a list, and then we just loop over the result array, and then this is a bit, perhaps not too Pythonic, but we need to create a table widget item for each item we insert. So table item consists of a string, and then you can also set the alignment here, how you want the contents of your cell to be aligned. So we set align right and align vertical center. Then we add them to our table. So this is the current row, and then we set the different columns here. And then finally, when we have all the data in a table, we can tell the table to resize to column contents. That means that it looks at what is in the table and resizes the columns to the right size. And you also have rows to the contents. It's not that important because it's by default. And here we just basically close the window. I also added some other functions that are perhaps not goes into a class, but some are useful for many of the classes here. Here is a try float method that we talked about in the last lecture. I also have a special function to query where we have our, if we install this application in some other location, how it will find its UI file. Some other stuff here that I go through here. This is something that is related to if we're running in PyQt5 and using Qt Creator, that it uses a different notation here. It will automatically replace certain things in the UI file that are not compatible with PyQt5. So I've implemented this here in this file. If you're using Qt6, this shouldn't be an issue. So, but that could be a good idea if you have functions in an application that kind of is not placed in its own class, or that you put them in a separate model and call it utils or something, and then you know that all the utility functions are in this. You have them organized. Don't spread them out in the user interface classes if they are not related to certain other class. You can just look at this is how the beam is stored in the JSON file. So you can see here that you have the lengths, you have the loads, you have the material properties, segment counts, and the support types. So using JSON, you get really nice input files for your simulation that you can actually edit without any problems. So I also use so if you I can show you here the main Beam application. It looks something like this in Qt Creator. So you can actually create all the menus directly here in Qt as well, and use reference and also the actions can be created. Let's see if I can find them in the bottom. You can see here that I have created actions here as well for each of the menu items here. And you can also add shortcuts here. So basically everything that can describe a user interface can be put in a UI file, which minimizes the amount of code that you have in your source code files. You can also create a resource file that contains the images of the controls. Let's see if I have it here. So yeah, we have to go to, let's see, add button here. You can see icon here, and I have a resource file here that is connected where I store all the files. So I can and then in the I can refer to that. I can also open this file. Open. This one. So this is a resource file, and here you can add your images to this file, and they're combined together into your can be used by a UI file instead of have separate image files. So here you can see I have my main layout, and here is where I insert my Beam widget. And then I also have something that is that you can do. It's a splitter, so you can have. So you can select that one. You can decide if you want something to be able to be movable between. You can select two groups, and then you can add a splitter in between here. So you go up here and you select splitter, and then you get a movable area. You can change the sizes here. So let's see if I can show you how that looks. Beam app there. So here, this is a splitter. So if you see that there's a bar here, if we go over, the mouse changes, and I can move this different ways here. I can even remove that if you want. You can control how much the relationship between those can be. In this case, you can see it that there is a minimum size of the widgets that controls some of the parts. So if you continue out here, it will collapse and go back again. And there is also a minimum of the left side here as well. So